Tonight, we're going to talk about the most distant machine humanity has ever built. Its name is Voyager 1. It launched in 1977 on a mission to explore the outer planets, and what it sent home changed the way we see the solar system forever. It gave us our first close-up look at the storms of Jupiter, swirling clouds larger than entire worlds. It revealed the rings of Saturn in breathtaking detail, thousands of delicate bands no one had ever seen before. And then it kept going, traveling past the planets and out toward the edge of everything. Today, it is more than 15 billion miles from Earth, drifting through the cold space between the stars, and it is still alive, still faintly whispering back to us across a gulf so wide its signal takes almost a full day to reach us. But there is one thing this remarkable machine no longer does. It no longer sees. The camera that captured all those unforgettable images was switched off back in 1990, and it has stared into darkness ever since. What would happen if we turned that camera back on and told Voyager 1 to look back at us one last time? What would it see? Would it see Earth? Would it see anything at all? By the end of tonight, you're going to understand exactly what Voyager 1 could show us from out there, why its camera was switched off in the first place, and why the view would be far stranger than you might expect. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand what Voyager 1's camera might see, we first have to understand where Voyager 1 actually is. And to understand that, we have to go all the way back to the very beginning. It launched on the 5th of September, 1977. When this spacecraft left Earth, there were no smartphones, no internet as we know it, no digital cameras tucked into anyone's pocket. The computers that fly Voyager 1 have less processing power and less memory than a basic greeting card that plays a tune when you open it. The total memory on board is measured not in the billions of bytes that fill a modern phone, but in mere thousands. And yet, that ancient machine is still working. It is still listening. Voyager 1 was not originally built to travel this far. It was designed for a mission that planners called the Grand Tour, made possible by a rare alignment of the outer planets that happens only about once every 176 years. In the late 1970s, the giant worlds of the outer solar system lined up in such a way that a single spacecraft could swing past several of them in succession, using the gravity of each planet to fling itself onward toward the next. This trick is called a gravity assist. A spacecraft falls toward a planet, borrows a little of that planet's enormous orbital motion, and is slingshot forward like a stone, whirled on a string, and then released. It costs almost no fuel, and it can add thousands of miles per hour to a spacecraft's speed in a single encounter. The mission planners realized that if they timed everything perfectly, they could reach the outer solar system in years instead of the decades it would otherwise demand. So two nearly identical spacecraft were built, Voyager 1 and Voyager 2, and they were sent out to explore the largest planets we had ever glimpsed. Voyager 1's primary targets were Jupiter and Saturn. Each spacecraft was, in essence, a science laboratory wrapped around a power source, bristling with instruments designed to measure magnetic fields, charged particles, radio waves, plasma, and all the invisible forces that fill the space between worlds. There was a long boom carrying sensitive magnetic field detectors held far from the body of the craft so the spacecraft's own electronics would not confuse the readings. There was a large dish antenna, almost 12 feet across, always kept pointed back toward the distant Earth, so that the faint stream of data would have somewhere to go. But the instrument that captured the public imagination, the one that made the whole world stop and stare, was the camera. The camera system on Voyager 1 was not a single camera, but a pair of them, mounted together on a movable platform that could swivel and tilt to aim at a chosen target. There was a wide-angle camera for capturing broad scenes, and a narrow-angle camera for zooming in on distant detail, almost like a powerful telephoto lens. Together, they were known as the Imaging Science Subsystem. Now, here is something worth pausing on, because it tells you just how old this technology really is. These cameras did not use the kind of digital sensor that sits inside every phone today. There were no megapixels. There was no memory card. Instead, each camera relied on something called a Vidicon tube, a small vacuum tube descended directly from the technology inside old television cameras. Light entered through the lens and struck a light-sensitive plate at the back of the tube, leaving behind a faint electrical pattern, a kind of ghost of the image. An electron beam then swept across that plate, line by line, reading off the pattern of light and shadow and converting it into a flowing electrical signal. That signal was turned into a long string of numbers, stored on a tape recorder on board the spacecraft, and then slowly trickled back to Earth as a stream of radio pulses. Each image was 800 lines tall, a fraction of the detail packed into even the most basic photo today, and it could take many minutes to read out and transmit a single frame. The cameras could not even see in color directly. To make a color picture, the spacecraft would photograph the same scene several times through different colored filters mounted on a spinning wheel, one frame through an orange filter, one through green, one through blue, and the separate images would later be combined back on Earth to recreate the true hues. It was slow. It was fragile. By the standards of today, it was almost laughably primitive. And yet, with this delicate and dated equipment, Voyager 1 took some of the most breathtaking photographs in the entire history of exploration. When Voyager 1 reached Jupiter in March of 1979, it sent home images that rewrote the textbooks. We saw the Great Red Spot up close for the first time, a storm so large that several Earths could fit inside it, swirling with bands of cream and orange and rust, a hurricane that has been raging for centuries. We saw Jupiter's atmosphere churning with detail no telescope on Earth had ever resolved, ribbons of cloud flowing in opposite directions, curling into eddies and knots at their boundaries. We saw a thin, faint ring circling the planet, something no one had known existed until Voyager looked and found it shining in the scattered sunlight. And then there were the moons. Jupiter is orbited by dozens of them, and Voyager turned its cameras on the largest with stunning results. On a small world called Europa, the cameras revealed a surface of bright ice, astonishingly smooth, crisscrossed by a tangle of long dark cracks, hinting at a hidden ocean of liquid water sloshing beneath the frozen shell. On Ganymede, the largest moon in the entire solar system, larger even than the planet Mercury, Voyager found ancient dark terrain scarred by craters, set against younger, grooved regions where the icy crust had shifted and refrozen. On Callisto, it saw a surface so heavily cratered that it had clearly been left almost untouched for billions of years, a frozen record of the solar system's violent youth. But the greatest surprise of all came from a moon named Io. As Voyager studied an image of Io taken against the blackness of space, a navigation engineer named Linda Morabito noticed something strange rising off the edge of the moon. A faint, umbrella-shaped cloud arcing high above the surface. At first, it seemed like an error, a trick of the light, perhaps another moon hiding behind. But it was real. It was a plume of material erupting from a volcano, and rising hundreds of miles into space. It was the first active volcano ever discovered beyond Earth. Io, it turned out, was the most volcanically active world in the entire solar system. Its insides kept molten by the constant gravitational kneading of mighty Jupiter. That single observation transformed our understanding of how alive and dynamic the outer solar system really is. These were not dead, frozen rocks circling a distant giant. They were active, evolving worlds, each with its own story, and Voyager 1 was the first eye ever to truly see them. After Jupiter, Voyager 1 used the giant planet's gravity to slingshot itself onward towards Saturn, arriving in November of 1980. If Jupiter had been a revelation, Saturn was a masterpiece. The cameras sent back the most detailed images of the rings anyone had ever seen, and they revealed that what had looked from Earth like a handful of smooth, simple bands were in fact made of thousands upon thousands of individual ringlets, nested one inside the next, like the grooves on a record. There were gaps where small moons had swept the ring material clear. There were faint dark spokes that appeared and vanished across the rings, mysterious features that seemed to defy the simple physics of orbiting particles. There was a thin outer ring, twisted and braided in a way that puzzled scientists for years. The rings, it became clear, were not a static decoration, but a living, churning system of countless icy fragments, ranging from grains of dust to boulders the size of houses, all circling the planet in an intricate gravitational dance. Saturn itself showed softer, more muted bands than Jupiter, wrapped in a pale golden haze, but no less beautiful for it. And then there was Titan, Saturn's largest moon, a world wrapped in a thick orange atmosphere far denser than our own. Scientists were desperate to know what lay beneath that haze. Could there be liquid on the surface? Could there be the chemistry that might one day lead to life? To find out, the mission planners made a fateful choice. They steered Voyager 1 onto a path that would carry it close past Titan for the best possible study of its atmosphere. But that close pass came at a steep price. The encounter with Titan bent Voyager 1's trajectory sharply, flinging it upward and out of the flat plane in which the planets travel. It was a bit like a car taking a hard exit ramp off a highway. From that moment on, Voyager 1 would never visit another planet. It would never see Uranus or Neptune up close, leaving those distant worlds for its twin, Voyager 2, to explore years later. Instead, Voyager 1 was thrown onto a path that pointed steeply up and out of the solar system, climbing away from the sun, away from the planets, and toward the open dark. Its planetary mission was finished. But its journey had barely begun. After Saturn, there was nothing left for the cameras to photograph. Ahead of Voyager 1 lay only empty space, growing emptier with every passing day. The planets fell behind. The sun shrank steadily in its rear view, and the spacecraft kept climbing outward at roughly 38,000 miles per hour, a speed that would carry it more than 10 miles in the time it takes you to read one of these sentences aloud. For most of the 1980s, the cameras sat idle and dark. There was simply nothing close enough to be worth a photograph. The instruments that measured fields and particles kept working, quietly recording the thinning influence of the sun. But the eyes of the spacecraft had little reason to open. And then one person decided that the cameras should look one last time, not for science, but for something deeper. His name was Carl Sagan, the astronomer and writer who had been part of the Voyager team from the very beginning, and who had a rare gift for helping ordinary people feel the wonder of the cosmos. Sagan had an idea, and it was not a scientific one. It was something closer to poetry. He wanted Voyager 1 to turn around. He wanted it to point its cameras back the way it had come, back across the billions of miles it had already crossed, and take a portrait of the entire solar system from the outside, looking in. A family portrait of the planets, including our own, as seen from the cold and distant edge of the neighborhood. It was not an easy request to grant. Pointing the cameras back toward the inner solar system meant aiming them perilously close to the sun, and staring at the sun could permanently burn out the sensitive Vidicon tubes, ending any chance of future imaging forever. There were also scientists and engineers who saw very little practical value in the idea. From this distance, the planets would appear as nothing more than faint, lonely dots. There would be no new measurements, no fresh data, no discoveries hidden in such a picture. From a purely practical standpoint, it seemed a waste of precious time, precious power, and the irreplaceable health of the cameras. But Sagan understood something that went beyond data. He understood that an image can carry a meaning that no column of numbers ever could. He believed that seeing our world rendered tiny against the immensity of space might change something in the way people thought about themselves, about each other, and about the fragile planet we all share. And after years of patient persuasion, the request was finally approved, scheduled for a time when the planetary mission was truly complete and the risk to the cameras no longer mattered. On the 14th of February, 1990, Voyager 1 turned its cameras toward home for the last time. By then, it was about 3.7 billion miles from the Sun, far beyond the orbit of Neptune, looking back across a distance that had taken it more than 12 years to travel. Over the course of several hours, it captured 60 separate frames, sweeping its narrow-angle camera across the inner solar system and photographing the planets one by one. It caught Venus, gleaming in reflected sunlight. It caught Jupiter and Saturn and the distant pale points of Uranus and Neptune. And it caught Earth. When the images were transmitted home over the following weeks and carefully assembled, one frame stood out above all the others. In it, our entire planet, everything that has ever happened to every person who has ever lived, appeared as a single point of light, less than the width of a single picture element. A pale blue dot, suspended by chance within a scattered band of sunlight, almost lost in the surrounding vastness. You could blot it out completely with the tip of a finger held at arm's length. Carl Sagan later wrote about that image in words that have echoed ever since. He reflected on how everyone you have ever heard of, every triumph and every sorrow in the long sweep of human history, all of it unfolded on that tiny speck hanging in a beam of light. He called it a mote of dust suspended in a sunbeam. He pointed out that all our conflicts, all our certainties, all our claims to importance look very different when you see how small the stage truly is. It was, and it remains, one of the most humbling images ever made by human hands. And then, having taken it, Voyager 1 closed its eyes. The decision to switch off the cameras came almost immediately after that final portrait. It was not a dramatic moment. There was no ceremony, no countdown, no farewell. The mission team simply sent a command, and the imaging system powered down for the last time. There were sound reasons for this, and they all point toward why turning the camera back on today would be so extraordinarily difficult. The first reason was distance. Voyager 1 was now so far from the Sun and racing farther every single day that there was genuinely nothing left worth photographing. Ahead of it lay only stars. And those stars are so impossibly distant that the cameras could never resolve them into anything more than the same faint points you can see on a clear night from your own backyard. In fact, a decent amateur telescope on the ground could show you those very same stars in far better detail than Voyager's aging cameras ever could from out there in the dark. The second reason was power. Voyager 1 does not run on sunlight. Out where it travels, the sun is far too weak and far too distant for solar panels to be of any use at all. Instead, the spacecraft carries a nuclear power source, a set of generators that produce electricity from the heat released by slowly decaying plutonium. When Voyager launched, these generators together produced several hundred watts, enough to run all of its instruments at once with power to spare. But that supply has been fading ever since. The plutonium decays a little more with each passing year, and the output drops by about 4 watts annually. 4 watts may not sound like much, but across nearly 5 decades, it adds up relentlessly. And out there, every single watt is precious beyond measure. By 1990, the team already understood that they would one day face hard choices about what to keep alive and what to let go. A camera that had nothing left to look at was, sadly, one of the easiest things to switch off. The third reason was a matter of memory and software. The cameras were controlled by special instructions stored in the spacecraft's tiny computers, and the routines needed to operate them and process their images took up valuable space in that minuscule memory. Engineers wanted to free up those scarce resources for the instruments that still had real work ahead of them, the ones designed to taste and measure the strange new environment of interstellar space. So the imaging software was, in effect, retired and set aside, no longer carried in the spacecraft's active memory. And here we arrive at the very heart of tonight's question. Because once those cameras went dark, turning them back on stopped being a matter of simply flipping a switch and became something far closer to impossible. So let's ask it directly. What if, today, we tried to turn Voyager 1's camera back on? What would actually happen? The honest answer is that it almost certainly would not work. And to understand why, we have to look carefully at everything that has changed in the long decades since that final photograph. Begin with temperature. Out where Voyager 1 drifts now, the cold is almost beyond human comprehension. The cameras were never designed to survive without their heaters, small electrical warmers that kept the delicate optics and electronics within the narrow range of temperatures in which they could function. As the available power has dwindled over the years, the Voyager team has been forced to switch off heater after heater, system after system, in a careful and painful process of triage, keeping alive only what is absolutely essential to the mission's survival. The heaters that once kept the camera platform warm were among the casualties long ago. That means the optics have now spent decades soaking in a cold that likely sits somewhere around -200 degrees Celsius, which is roughly -330 degrees Fahrenheit, far colder than anything found naturally on the surface of our own planet. Glass and metal do not respond gently to that kind of chill. The lubricants that once allowed the camera platform to swivel and aim may well have frozen solid. The lenses themselves may have cracked under the relentless cold. The fine mechanisms that focused and pointed the cameras may be seized permanently in place, never to move again. Even if every other system were somehow perfect, the simple physical act of aiming the camera back toward Earth might now be flatly impossible. Then there is the problem of the software and the lost knowledge. The instructions that told the cameras how to operate, how to set an exposure, how to read an image off the Vidicon tube, how to package the data for the long journey home, were cleared from the spacecraft's active memory long ago to make room for other tasks. The engineers who originally wrote that software, who knew its every quirk and secret, have in many cases retired, and some are no longer with us. The specialized ground equipment that was once used to command the cameras and receive their images was dismantled and repurposed decades ago. The very knowledge of how to speak to those cameras now survives, mostly in aging paper documents, in fragile old data tapes, and in the memories of a handful of people. Reviving it would be a monumental undertaking, reconstructing lost code, rebuilding lost procedures, and somehow squeezing it all back into a computer with less memory than a modern doorbell. A computer that is already stretched to its limits, keeping the spacecraft alive. And even if all of that could somehow be accomplished, it would consume power and attention that the mission simply cannot spare. Consider, too, the sheer slowness of any conversation with Voyager 1. Every command sent to the spacecraft now takes the better part of a day just to arrive. The spacecraft is so far away that a radio signal traveling at the speed of light, the fastest thing in the universe, needs around 22 to 23 hours to reach it. In late 2026, Voyager 1 will cross a remarkable threshold that no human-made object has ever reached before. It will be one full light day from Earth, a distance of about 16 billion miles, the distance light itself travels in a single day. At that point, if engineers send a command on a Monday morning, the spacecraft does not even receive it until the following day, and its reply does not arrive back at Earth until the morning after that. A single simple exchange takes 2 days from beginning to end. There is no real-time control out there. There is no quick correction if something goes wrong. There is only patience and a lot of waiting. And lest you think the spacecraft's electronics are simply frozen in time, waiting patiently to be commanded, consider what happened just a couple of years ago. In late 2023, Voyager 1 suddenly began sending home a stream of meaningless data, a repeating pattern of ones and zeros that carried no information at all. The spacecraft was still alive, still transmitting, but it had, in effect, lost the ability to speak clearly. For months, engineers on the ground worked the problem with almost nothing to go on, sending careful commands and waiting nearly 2 full days each time to learn whether anything had changed. Eventually, they traced the trouble to a single small piece of failing memory in one of the spacecraft's computers. A tiny chip that had given out after nearly half a century of faithful service. Because the affected memory could no longer be used, the team had to take the software stored there, break it into pieces, and carefully relocate those pieces into other parts of the computer's memory that still worked, all while the patient sat more than 15 billion miles away. In the spring of 2024, the fix worked. Voyager 1 began speaking clearly again, sending home usable data for the first time in months. It was a stunning feat of long-distance repair, a group of engineers reaching across the Gulf to mend a machine older than most of them, using instructions that took most of a day just to arrive. But the episode is also a quiet warning. The spacecraft is fragile and aging. Its memory is failing piece by piece. This is not a machine you would want to risk by reawakening a long-dead camera system and demanding it perform a task it was never expected to do again. But let's set all of that aside for a moment. Let's imagine, just for tonight, that none of these obstacles existed. Let's imagine that by some miracle, the heaters had kept the optics perfectly warm, that the software still lived intact in memory, that the platform could still turn freely, that the failing chips had held, and that we had the power and the patience to spare. Let's imagine we could actually command Voyager 1 to open its eye and look back at us, right now, tonight. What would it see? This is where the answer becomes strange and a little heartbreaking. It would see almost nothing. Voyager 1 is now more than 15 billion miles from home, and at that staggering distance, the entire inner solar system has collapsed into a tiny, tight little knot of faint points huddled close around the sun itself. That overwhelming presence that fills our daytime sky and gives us all our warmth and light and the very rhythm of our days would no longer appear as a disk at all. It would be a single brilliant star. Bright, yes, the brightest point in all of Voyager's sky, but a point nonetheless, something you could hide completely behind a fingertip held at arm's length. And Earth. Earth would be hopelessly, utterly lost. In 1990, when Voyager took the pale blue dot, our planet was already less than a single picture element wide. It was visible at all only because Voyager was still relatively close, and only because the geometry of that moment happened to be just right, with sunlight scattering in a way that lit our world like a tiny ember. Today, from more than 4 times that distance, Earth would be drowned completely in the glare of the nearby sun. The camera could not possibly separate the faint dot of our world from the blinding point of our star sitting right beside it in the frame. The picture, if we could even take it, would show a scattering of stars and one slightly brighter star among them. And that single brighter star would be everything. It would be the sun, and the Earth, and every planet, and every ocean, and every mountain, and every person who has ever lived, all compressed into one unremarkable speck of light, indistinguishable from the background of the galaxy. To anyone who did not already know the truth, it would look like nothing more than an ordinary, forgettable patch of sky. There is something quietly devastating about that realization. Voyager 1 has traveled so far that home is no longer even a recognizable feature in its view. The sun that warmed the world that built it, the star that launched it and guided its every maneuver across the planets, has shrunk to just another point of light in a field of countless points. If Voyager could feel, and of course it cannot, it would have no way of knowing which of those distant lights was the one it came from. This is what genuine cosmic distance really means. Not the distance between cities, or even the distance between planets, but the distance at which your entire origin, your whole world, your sun, your everything, becomes invisible against the wider universe. The pale blue dot was already a profound lesson in how small we are. A photograph taken today would be an even harsher lesson, a reminder of how small even our sun becomes against the backdrop of the galaxy. And this, in the end, is the deeper reason the cameras were never meant to come back on. There is nothing out there for them to see that would carry any real meaning. The story Voyager 1 has to tell us now is not a visual story at all. It is a story written entirely in the invisible. Because while the cameras fell silent decades ago, Voyager 1 itself has never stopped exploring. It simply traded its eyes for other senses, and with those other senses, it has made discoveries that no camera could ever have captured. To appreciate them, we need to understand the strange series of boundaries the spacecraft has crossed on its long climb out of the solar system. Picture the sun not just as a source of light, but as a source of wind. The sun constantly blows out a steady stream of charged particles in every direction, a continuous gale called the solar wind, racing outward at hundreds of miles every second. This wind pushes through space, carving out an enormous bubble around the Sun and all of its planets, a vast region where the Sun's influence reigns. That bubble is called the heliosphere, and for the entire history of our species, everything we have ever known, touched, or sent into space has lived comfortably inside it. The first boundary Voyager 1 reached is called the termination shock. This is the place where the solar wind, after racing outward for billions of miles, suddenly slams into the thin gas of interstellar space and abruptly slows from its supersonic rush. Voyager 1 crossed this turbulent boundary in December of 2004, far beyond the orbit of the most distant planet, and its instruments recorded the dramatic slowing and piling up of the solar wind as it crossed. Beyond the termination shock lies a vast, sluggish region called the heliosheath, where the solar wind grows slow and hot and turbulent, like the churning froth at the edge of a great river meeting the sea. Voyager 1 spent years crossing this region, far longer than anyone had predicted, slowly working its way toward the true edge. And then, in August of 2012, it reached the final boundary, the heliopause. The heliopause is the outer skin of the Sun's great bubble, the place where the solar wind finally runs out of strength entirely and gives way to the thin gas and particles that drift between the stars. When Voyager 1 crossed it, it became the first object ever built by human hands to leave the Sun's bubble and enter true interstellar space, the space between the stars. It did not detect this historic crossing with a camera. It detected it with its instruments, in the language of particles and fields. The density of the plasma surrounding the spacecraft suddenly jumped by a large factor, climbing to the higher values expected in interstellar space. The number of charged particles streaming outward from the Sun fell away sharply, replaced by the higher energy cosmic rays that are born in the violent deaths of distant stars and roam freely through the galaxy. The direction and character of the surrounding magnetic field shifted in subtle but measurable ways. Voyager 1 had, in the most literal possible sense, sailed out of our local harbor and into the wide open ocean of the galaxy. It is worth being careful here. Crossing the heliopause does not mean Voyager 1 has left the solar system entirely, not in the way most people imagine. The Sun's gravity still reaches far, far beyond this point, out to a distant cloud of icy bodies that the Sun loosely holds in its grip. Voyager 1 will take tens of thousands of years just to begin passing through that distant region. But it has left the bubble of the Sun's wind, and in that meaningful sense, it has crossed into the realm between the stars, somewhere no human creation had ever been. Out there, in the space between the stars, the environment is unlike anything found inside the heliosphere. It is not perfectly empty. There is a thin gas, called the interstellar medium, made of atoms and charged particles, spread so sparsely that there might be only a fraction of a single particle in a volume the size of a small room. By any earthly standard, that is a vacuum far more perfect than anything we can create in even our finest laboratories. And yet, it is not lifeless or still. It is threaded with magnetic fields, washed by waves of energy from distant cosmic events, and stirred by the slow churning of the galaxy itself. Voyager 1 has been listening to this medium with remarkable patience. One of its instruments measures the density of the plasma around the spacecraft. By detecting the way that plasma vibrates and rings when it is disturbed, almost like the way a bell sings out a particular note when it is struck. In the years following its crossing into interstellar space, the spacecraft repeatedly heard the surrounding plasma ring in response to powerful bursts of energy that erupted from the sun. Waves that took many months to travel all the way out and wash over it. In a strange and quietly beautiful way, Voyager 1 has been hearing the faint song of the space between the stars. A song no instrument had ever heard before, simply because nothing we had ever built had been there to listen. More recently, its instruments have detected something even subtler, a faint, steady hum in the interstellar gas. A constant low signal that seems to be the background ringing of the medium itself, persisting even when the sun is quiet. It is as though, after crossing into the great dark, the spacecraft can hear the steady, distant murmur of the galaxy. This is the work it does now. Not pictures, but measurements. Not portraits of worlds, but the faint and patient recording of the conditions in a place no human will visit for countless generations, if ever at all. It is worth sitting for a long moment with just how alone Voyager 1 truly is out there. The nearest star to our Sun is a small dim red dwarf called Proxima Centauri, and it lies about 4.2 light-years away. A light-year is the distance light travels in a single year, and light is so fast that it could circle the entire Earth more than 7 times in 1 second. To cross 4.2 light-years at the speed of light would still take more than 4 years. Voyager 1, for all its impressive speed, travels nowhere near the speed of light. It moves at roughly 10 miles every second, which is breathtakingly fast by any human standard, and yet almost nothing on the scale of the stars. If Voyager 1 were aimed directly at Proxima Centauri, which it is not, it would take roughly 70,000 years to arrive. That is far longer than the entire span of recorded human civilization, stretched out many times over. The spacecraft is not headed toward Proxima at all. It is climbing up and out of the flat disk of our galaxy in its own particular direction, and the nearest star it will eventually pass is a quiet, faint sun called Gliese 445 in the direction of a northern constellation. In about 40,000 years, Voyager 1 will drift within roughly 1.6 light-years of that star. It will not stop there. It will not be captured by its gravity. It will simply pass by in the dark, a tiny artificial speck sailing silently through the distant outskirts of a stranger's solar system, and then continue onward into the deeper galaxy beyond. By the time it makes that distant pass, the spacecraft will already have been silent and powerless for tens of thousands of years. Its nuclear source will long since have faded to nothing. Its instruments will have gone cold and quiet. It will be nothing more than a dark, frozen, drifting object, carrying with it a single, enduring message from the world that made it. Because Voyager 1 does carry one last thing, something placed aboard precisely for a future this unimaginably distant. Bolted to the side of the spacecraft is a golden phonograph record, a disc of gold-plated copper covered in fine grooves, very much like an old vinyl record from the era in which it was launched. It was placed there deliberately as a message in a bottle, cast into the cosmic ocean on the slim and wondrous hope that someday, somewhere, something might find it and understand. On that record is encoded a small portrait of our entire world. There are spoken greetings in 55 different languages, voices from across the earth offering words of welcome and goodwill to whoever might one day listen. There are the sounds of our planet, carefully gathered, wind and thunder and surf, the songs of birds, the calls of whales, the patter of rain, footsteps, a beating heart, the laughter of a person, and the cry of a newborn child. There is music, more than 90 minutes of it, drawn from many cultures and many centuries, from classical compositions to folk songs to the rhythms of peoples all around the globe. And there are images, more than 100 of them, encoded as patterns in the grooves, showing what we look like, how we are built, where we live, what we eat, and where our small planet sits among its neighbors. The cover of the record is itself a kind of message, etched with diagrams meant to be understood by a mind that shares none of our language or culture. There are instructions, drawn in simple scientific symbols, explaining how to play the record and at what speed. And there is a map. Not a map of streets or countries, but a map of the sky, showing the position of our sun relative to 14 distant, rapidly spinning stars called pulsars, each one flashing at its own precise rhythm. By reading off those rhythms, a sufficiently advanced finder could, in principle, trace their way back across the galaxy to the very place this object began its journey. The record was designed to endure almost beyond comprehension. In the near-perfect emptiness of interstellar space, there is no weather to wear it down, no oxygen to corrode it, no rain or wind or hand to disturb it. The people who created it estimated that it could remain readable for 1 billion years or longer. That is far longer than complex life has even existed on Earth. Think carefully about what that truly means. Long after our sun has swollen into a vast red giant in some 5 billion years, scorching and likely swallowing the inner planets, long after the Earth as we know it is gone, that golden record will still be drifting through the galaxy. It will still carry the sound of a child laughing, the song of a whale, and the image of a small blue world that once was home to everything we have ever loved. The camera that took the pale blue dot will by then be cold and dead and forgotten. But the record will endure, a single fingerprint of our existence pressed into gold and flung across the dark for a span of time we can barely even name. So, when we ask what Voyager 1's camera would see if we somehow turned it on tonight, we are really asking something far larger than a question about an old machine. We are asking what it means to look back. We are asking whether there is anything left worth seeing once you have traveled so far that your entire home has shrunk to a speck and then vanished completely into the glare of a single distant star. And the answer, strangely, is yes. There is still something left to see. But the camera is simply the wrong instrument to see it with. What Voyager 1 reveals to us now is not visible at all. It reveals the true shape of our place in the galaxy by measuring exactly where the sun's influence ends and the wider cosmos begins. It reveals the hidden texture of interstellar space by listening to it ring and hum. It reveals the raw, staggering scale of distance simply by being, itself, the most distant thing our species has ever touched. The most important picture Voyager 1 ever took was not of a planet, or a moon, or a ring. It was the pale blue dot, an image that contained almost no scientific information at all, and yet changed how millions of people understood their own existence and their own world. That photograph did not really show us the universe. It showed us ourselves, reflected back from the edge of the dark, and it reminded us how small and how rare and how precious that little world truly is. A second picture, taken today, could never match it. It would show only a field of indifferent stars, with the whole of our reality hidden invisibly inside one of them. But perhaps that, too, is a kind of message worth carrying. Perhaps the lesson of a photograph we can no longer take is that we have already journeyed far enough to lose sight of home entirely, and that the only home we will ever truly have is the one we can no longer even pick out from out there in the cold. There is one more thing worth understanding about the years that lie ahead for this remarkable machine. Voyager 1 is fading, slowly, not in a single dramatic failure, but gradually, inch by inch, watt by watt. Every year, as its nuclear source weakens, the team on the ground must make a quiet, difficult decision about what to switch off next. Instruments that have run faithfully since the 1970s are being powered down one by one, not because they have broken, but simply because there is no longer enough electricity to feed them all. Heaters that protect those instruments from the deadly cold are being sacrificed to keep the most important systems alive just a little longer. The engineers who care for the spacecraft often describe their work as tending to a beloved elder, doing everything within their power to extend a precious life while gently accepting that the end is drawing nearer with each passing year. Sometime in the coming years, very possibly within this decade, Voyager 1 will no longer have enough power to run even a single one of its scientific instruments. After that, it may continue sending faint engineering signals for a while longer, simple confirmations that it is still alive, still moving, still out there in the dark. And then, at last, even those will cease. The final signal will leave the spacecraft, travel for the better part of a full day across the emptiness, and arrive at Earth as a whisper almost too faint for our largest antennas to hear. The great dishes will listen, and one day there will be only silence on the other end of the line. But silence is not the same as gone. When the last signal fades, Voyager 1 will not stop. It will keep moving, exactly as it has for nearly half a century, coasting outward at tens of thousands of miles per hour. Carried by momentum, it gathered from giant planets. It visited a lifetime ago. It needs no power at all to travel. It needs no commands to continue on its way. It will simply drift, on and on and on, through the dark between the stars, for millions of years, then billions, long after everyone who built it is gone, long after the very story of how it came to be has been forgotten by whatever comes after us. And it is worth pausing to consider just how faint our connection to Voyager 1 has already become. The spacecraft transmits its data using a radio transmitter with a power of only about 20 watts, roughly the same as a dim household bulb. That faint whisper of a signal then spreads out across more than 15 billion miles of space before a tiny sliver of it finally reaches Earth. By the time it arrives, the signal is so unimaginably weak that it carries a fraction of a billionth of a single watt. To capture something so faint, we use enormous dish antennas, some of them more than 200 feet across, spread around the world so that as the Earth turns, one of them is always able to face the spacecraft. These great dishes are part of a network built specifically to stay in touch with our most distant explorers, and even they strain to hear Voyager's failing voice. It is one of the quiet wonders of this whole story, that across such an unfathomable gulf, with a transmitter no more powerful than a nightlight, we can still hear a machine launched before most people alive today were born. And it can still hear us. That thread of contact, thin as it is, connects our warm and crowded planet to a cold, lonely traveler at the very frontier of everything we have ever reached. For now, that thread still holds. But it grows thinner every year, and one day, gently, it will finally let go. To truly appreciate what that sleeping camera means, it helps to go back and walk through the journey more slowly. Because the more you understand about how Voyager 1 came to be, the more astonishing its silence at the edge of the solar system becomes. Consider the morning of the launch itself. Voyager 1 actually left Earth after its twin, despite the lower number in its name, riding atop a powerful rocket from a launch pad in Florida. The rocket roared upward through the atmosphere, shed its spent stages one by one, and finally flung the spacecraft onto a path that would carry it across the solar system faster than anything that had reasonably come before on such a long road. In those first hours, the spacecraft unfolded itself into its working shape, extending its long booms, locking its great dish antenna into position, and turning its instruments on for the first time in the cold of space. And then it looked back. Just a couple of weeks after launch, while still relatively close to home, Voyager 1 turned its cameras around and captured something that had never been done before in quite that way. It photographed the Earth and the Moon together in a single frame, both worlds hanging in the blackness, the bright blue Earth and its smaller grey companion caught in the same image for the very first time. It was a small preview of everything to come, a hint that this machine was not only a scientific instrument, but a kind of mirror, capable of showing us ourselves from vantage points no human had ever occupied. From there, Voyager 1 settled into the long cruise toward Jupiter, a journey of more than a year and a half across hundreds of millions of miles of empty space, with the sun slowly shrinking behind it and the giant planet growing slowly brighter ahead. It is easy to forget, when we speak of cameras and photographs, just how extraordinary the spacecraft carrying them really is as a piece of engineering. Voyager 1 was built to think for itself, at least a little, because at the distances it would travel, no human could possibly react quickly enough to save it from trouble. It carries a set of small computers, primitive by any modern measure, that work together to run the spacecraft, point the antenna, aim the instruments, and watch over the craft's own health. These computers were given a kind of simple wisdom that engineers call fault protection. If something goes wrong, if a system fails, or the spacecraft loses track of where it is pointing, the computers are designed to recognize the trouble, shut down whatever is not essential, and quietly place the spacecraft into a safe, stable state, all on their own, without waiting for instructions that might take a full day to arrive. Then they turn the antenna back toward the distant sun, find their bearings, and call home to report what has happened. This ability to look after itself has saved Voyager 1 more than once across its long life. The spacecraft also keeps its bearings using the stars themselves. It carries a small sensor that locks onto a single bright reference star, using that fixed point of light to know exactly how it is oriented in the blackness, much as ancient sailors once used the stars to steer across featureless oceans. For decades, this quiet partnership between simple computers and the steady light of distant stars has kept the spacecraft's antenna aimed back at the tiny, pale point that is home, ensuring that its faint voice always has a direction in which to travel. When you understand all of this, the spacecraft stops being a mere object and starts to feel almost like a living traveler, patient, careful, and quietly determined to survive. Now, think again about Jupiter, because what Voyager 1 endured there is part of why its survival to this day feels so remarkable. Jupiter is not only the largest planet in the solar system, it is also surrounded by the most intense and dangerous radiation environment of any world we know. The giant planet is wrapped in an enormous magnetic field, far larger and far stronger than Earth's. And trapped within that field are belts of charged particles moving at tremendous speeds, capable of damaging delicate electronics in a matter of hours. When Voyager 1 dove in toward Jupiter to make its observations, and to use the planet's gravity for its slingshot, it had to pass through a portion of this fierce radiation. The spacecraft absorbed a dose far higher than it had been designed to withstand, and some of its systems were briefly affected, but it emerged on the other side, battered yet alive, carrying its precious cargo of images and measurements. Among the discoveries at Jupiter was a vast donut-shaped ring of glowing gas circling the planet along the path of the volcanic moon Io. This ring, born from the material that Io's volcanoes hurl into space, traces out an invisible river of particles fed continuously by that restless little world. Voyager also measured Jupiter's powerful auroras, glowing curtains of light at the planet's poles, far brighter and more energetic than the gentle auroras that dance in Earth's polar skies. And it detected lightning flashing in Jupiter's clouds and the crackle of radio noise pouring off the giant planet, a world alive with energy on a scale that dwarfs our own. All of this, captured by a machine that then turned and flew onward, leaving the giant behind forever, climbing toward its next and final planetary encounter. At Saturn, the encounter was brief but extraordinarily rich. Voyager 1 swept through the Saturn system over a span of just a few days, but in that short window, it gathered observations that scientists would study for decades afterward. It measured the fierce winds in Saturn's atmosphere, far swifter than any winds on Earth, racing around the planet at speeds that would be unimaginable in our own skies. It studied the planet's faint internal heat, discovering that Saturn, like Jupiter, radiates more energy than it receives from the distant sun, a sign of processes still at work deep inside. It turned its cameras on Saturn's many moons and found a remarkable variety of frozen worlds. There was Mimas, a small moon marked by an enormous impact crater, so large it gives the little world the look of a single great eye. There was Rhea and Dione and Tethys, each an icy sphere bearing its own pattern of craters and bright streaks. And there was Enceladus, a brilliant white moon whose smooth, reflective surface hinted that something had resurfaced it in the relatively recent past, a clue that would only deepen into mystery as later missions revealed its secrets. But it was Titan, shrouded in its thick orange haze, that most fascinated the mission planners and that ultimately decided Voyager 1's fate. The choice to fly close past Titan, to probe that mysterious atmosphere, was the choice that lifted Voyager 1 up and out of the plane of the planets and aimed it at the empty space beyond. In a sense, Titan was both the spacecraft's last great destination and the doorway through which it left the familiar solar system behind. After that final encounter, Voyager 1 had visited its last world, and every image it would ever take of a planet had already been taken. Imagine, for a moment, that the cameras had never been switched off. Imagine that Voyager 1 had kept its eye open through all the long years since Saturn, taking a single photograph of the sun behind it every so often, all the way out into the dark. At first, in the years just after Saturn, the sun would still have appeared as a small but distinct disk, painfully bright, clearly more than a mere point. But year after year, that disk would have shrunk. By the time the spacecraft reached the distance where it took the pale blue dot, the sun had already collapsed to something closer to a brilliant star than a disk you could resolve. And in the decades since, in our imagined unbroken film, the sun would have continued to dwindle, growing fainter and smaller against the unchanging field of background stars. Until today, it would be just one more point of light, brighter than the rest, but no longer special to the eye. Such a film would be the truest portrait of distance ever made, a slow, silent shrinking of everything we are into a single fading spark. It would show, frame by frame, the experience of leaving home so completely that home itself disappears. This is what makes the silence of the real cameras feel so poignant. That imagined film does not exist, and it never will. The cameras closed their eye while the sun was still bright enough to wash out the earth, and from that day forward, the long shrinking of our world into the cosmic background has gone unwitnessed, recorded by no one and nothing, happening only in the cold geometry of the spacecraft's ever-growing distance. Even setting aside the frozen optics and the lost software, there is another quiet obstacle that would stand in the way of any new photograph, and it has to do with how slowly Voyager 1 can now speak. When the spacecraft was exploring the planets, it could send its data home at a healthy rate, fast enough to return detailed images within a reasonable time. But as the spacecraft has receded into the distance, the rate at which it can transmit usable information has fallen dramatically. Today, Voyager 1 sends its data home at a trickle, a rate so slow that it is measured in mere tens or hundreds of bits each second, slower than the very earliest home internet connections that some of us still remember. At such a glacial pace, a single high-quality image, made of many hundreds of thousands of individual pieces of information, would take an enormous amount of time to transmit back across the void, tying up the great antennas on Earth and the spacecraft's dwindling power for a result that would show, as we have seen, almost nothing at all. There is also the problem of holding perfectly still. To take a sharp photograph of a faint and distant target, the camera must be aimed with extraordinary precision and held rock-steady while the image is gathered. A spacecraft drifting and gently rotating in the dark, with its pointing systems aged and its supply of maneuvering gas slowly running low, would struggle to hold the kind of steady aim that a clear picture demands. The image, even if everything else worked, would likely be smeared and blurred, a faint streak rather than a clean point. Every part of this old machine, from its frozen lenses to its sluggish voice to its unsteady aim, now conspires to make that one last photograph impossible. The universe, it seems, has gently closed that door. It is worth understanding the quiet, steady heart that has kept Voyager 1 alive through all of this, because it is one of the most remarkable parts of the whole story. The spacecraft is powered by a set of devices that turn heat directly into electricity, with no moving parts at all. Inside, each one sits a quantity of a special material, a form of plutonium that is intensely radioactive and, as a result, naturally warm to the touch, glowing a faint red with its own heat. This material steadily releases energy as it decays, and that heat is converted into a modest flow of electricity by banks of devices that produce a current whenever one side is hot and the other side is cold. It is a beautifully simple idea, with nothing to wear out or break down, which is exactly why it can run for decades in the depths of space where sunlight is far too weak to be of any use. But the plutonium does not last forever. It decays at a steady, predictable pace, losing half of its strength over a span of roughly 87 years, and as it weakens, so too does the warmth it provides and the electricity that warmth can generate. This is the slow, unstoppable clock that governs Voyager 1's life. Every year the heat grows a little fainter, the electricity a little scarcer, and the team must let go of one more piece of the spacecraft to keep the rest alive. There is something almost tender about it, a machine kept warm and awake by the slow fading glow of a tiny radioactive heart, a heart that has been quietly cooling since before most people watching this were born, and that will, before too many more years have passed, finally grow too cold to sustain even a whisper. The discoveries Voyager 1 has made out beyond the planets have reshaped our understanding of the boundary between the Sun's realm and the wider galaxy. Before Voyager crossed it, no one truly knew what the edge of the Sun's great bubble would look like, or even exactly where it lay. As the spacecraft approached the heliopause, it passed through a strange transitional region that scientists came to call the magnetic highway, a place where the Sun's magnetic field connected outward to the field of interstellar space, allowing particles to stream along the field lines like cars along a road. Within this region, the spacecraft watched the Sun's particles drain away while the high-energy cosmic rays from the wider galaxy poured in, a clear sign that the true edge was near. When at last it crossed into interstellar space, Voyager revealed that the boundary was sharper and more abrupt than many had expected. A relatively thin skin separating two very different realms. It also discovered that the interstellar magnetic field just outside the bubble was oriented in a surprising direction, raising new questions about the shape of the heliosphere and how it is squeezed and sculpted by the galaxy around it. These are not findings that any camera could have captured. They live entirely in the realm of fields and particles, in the subtle readings of instruments designed to feel rather than to see. And they remind us that the most important frontier Voyager 1 crossed was an invisible one, a boundary you could pass straight through without seeing anything change at all. And yet, a boundary that marks the true edge of the Sun's dominion over space. Let us return, too, to that golden record, because the story of how it came to be is as moving as anything the spacecraft has done. In the months before launch, a small group of people was given an almost impossible task. They were asked to decide what humanity should say about itself to the entire universe, and to fit that statement onto a single record that might outlast the Earth itself. The team was led by Carl Sagan, the same man who would later argue for the pale blue dot, and it included a young woman named Anne Druyan, who served as the creative director responsible for choosing the sounds and music of Earth. Together, they pored over the sounds of the world, choosing what to include and what to leave behind, trying to capture the texture of life on our planet in a handful of recordings. They selected music spanning continents and centuries, from grand orchestral works to simple folk melodies, hoping to convey something of the beauty and variety of human expression. They gathered greetings in language after language, and the sounds of nature and of human life, the surf and the wind, the animals and the machines, the laughter and the footsteps. And in one quietly extraordinary act, Anne Druyan had her own brainwaves and heartbeat recorded while she sat and let her mind wander through thoughts of the history of the Earth, of human struggle, and, as it happened, of the man she had recently fallen in love with, Carl Sagan himself. That recording of a human mind in a moment of wonder and affection was encoded into the record, so that some future finder might, in principle, hold within their hands the patterns of a person's thoughts on a day when she was newly in love. It is a love letter, in the most literal sense, carried out among the stars. The team also included a small sample of a radioactive element on the record's cover, so that any finder could measure how much of it had decayed and thereby work out how long the record had been traveling through space. A built-in clock counting down the eons. When you remember that this record rides on the side of Voyager 1, just inches from the sleeping camera, the whole spacecraft takes on a deeper meaning. It is not merely an explorer. It is a messenger, carrying the carefully chosen voice of an entire world out into a silence so vast that the message may never be heard by anyone at all. And what are the chances that it ever will be heard? Honestly, they are vanishingly small, and the people who built the record knew this from the start. Space is almost incomprehensibly empty, and Voyager 1 is almost incomprehensibly tiny against that emptiness. It is not broadcasting its location, it is not heading toward any particular star, and it will drift for tens of thousands of years before it even passes near another sun. And even then, it will pass at a distance far greater than the span of our entire solar system. For some alien intelligence to find it, they would have to stumble across a small, dark, silent object, barely larger than a car, somewhere in the immense ocean of the galaxy, purely by chance. And by the time that could happen, the spacecraft's power will have failed, its signals will have ceased, and only the durable golden record will remain readable. The record, then, was never really launched with a realistic hope of being found. It was launched as a statement, a gesture, a message in a bottle thrown into a cosmic ocean so wide that the bottle will almost certainly drift forever. It says, simply, that we were here. It says that on a small blue world, circling an ordinary star, there once lived beings who thought and felt, who made music and fell in love, who looked up at the night sky and wondered what was out there, and who reached out into the dark with the best and most hopeful version of themselves. In a very real way, the record was made more for us than for any alien. The act of deciding what to say to the universe forced its creators, and forces all of us, to ask what truly matters about being human, what is worth preserving, what we would want to be remembered by if we had only one chance to speak. That reflection is itself a kind of gift, regardless of whether the message is ever received. Voyager 1 is not entirely alone in carrying humanity outward, though it is the farthest of its small fellowship of distant travelers. Before the Voyagers, two earlier spacecraft, named Pioneer, were sent on their own journeys toward the outer planets and beyond, each carrying a simple engraved plaque rather than a record, a quieter and simpler message bolted to its frame. Those Pioneer spacecraft have long since fallen silent, drifting now without power on their own paths into the galaxy, no longer able to speak to us, but still carrying their plaques outward. Voyager 1's twin, Voyager 2, followed its own route through the outer solar system, becoming the only spacecraft ever to visit the distant ice giants, and it too has now crossed into interstellar space, traveling in a different direction through the dark, carrying its own copy of the golden record. And a newer explorer, launched decades later to study the dwarf world at the solar system's edge, is now also climbing outward, destined one day to join this tiny, scattered family of objects that have left the sun's neighborhood for good. Together, these handful of spacecraft represent the leading edge of human presence in the galaxy. The very first physical things our species has ever sent permanently beyond our own cosmic doorstep. They will outlast our buildings and our monuments, our languages and our nations, perhaps even our species itself. Long after every other trace of us has faded, these silent travelers will still be moving through the dark, carrying their plaques and their records, the most enduring artifacts our civilization has ever made. Among them all, Voyager 1 leads the way, the farthest and the fastest, the first to cross into the space between the stars, and the one carrying that sleeping camera which once showed us our whole world as a single point of light. There is, finally, a deeply human story woven through all of this, one that is easy to overlook when we focus on the machine. Voyager 1 has been flying for so long that it has outlived many of the people who built it and first commanded it. The engineers and scientists who launched this spacecraft in the 1970s were young then, at the start of their careers, and many have since retired or passed on. The mission has been carefully handed down across generations, from the people who first dreamed it up to those who guided it past the planets, to the small dedicated team that watches over it today, listening for its faint voice and making the hard decisions about how to keep it alive. Some of the engineers now caring for Voyager 1 were not even born when it launched. They have devoted their working lives to a machine that left Earth before they existed, learning its quirks from old manuals and the memories of their elders, treating it with the patience and respect one might give to a wise and fragile ancestor. There is something profoundly moving in that continuity, in the way knowledge and care for this distant traveler have been passed from hand to hand across half a century. It is a reminder that great endeavors outlast individual lives, that a project begun by one generation can be carried forward by the next, and the next, each adding their care to a story far longer than any single human span. When the day finally comes that Voyager 1 falls silent for good, it will mark not only the end of a spacecraft, but the closing of a chapter that has connected several generations of dreamers, builders, and caretakers, all bound together by a single small machine drifting at the edge of everything. It is worth trying, just once, to feel the true size of the distance involved, because numbers alone tend to slide off the mind. Voyager 1 is more than 15 billion miles away. Light, the fastest thing that exists, the thing that crosses from the Sun to the Earth in about 8 minutes, now needs nearly a full day to make the same trip out to Voyager 1. When you look up at the Sun and feel its warmth, you are feeling light that left it 8 minutes ago. But a beam of light leaving the Sun right now, at this very instant, would not reach Voyager 1 until this time tomorrow. That single fact, more than any string of digits, captures the gulf that the spacecraft has opened between itself and the world that made it. And still, it pulls farther away with every second, adding another 10 miles, and another, widening the gap in the time it takes to draw a breath. There is a loneliness to that which is hard to put into words. No object made by human hands has ever been so far from all the others. If you could somehow stand beside Voyager 1 and look back, you would not see the Earth. You would not see the planets. You would not even see the Sun as anything more than a bright star among a scattering of others. You would simply be surrounded, in every direction, by the deep and patient dark, with the nearest true companion star still trillions of miles away. This is the place from which we are imagining turning a camera back toward home. This is how far our reach has extended, and how small that reach still is against the scale of the galaxy. The simple fact that we can still hear from Voyager 1 at all depends on a quiet, sprawling effort that most people never think about. To stay in touch with our most distant spacecraft, we built a network of enormous radio dishes placed at 3 sites spread roughly evenly around the world. One in the deserts of the American Southwest, one near the Spanish capital, and one in the countryside of eastern Australia. These 3 sites are positioned so cleverly that as the Earth turns on its axis, at least one of them is always able to face any given point in deep space. When one dish rotates out of view as our planet spins, another swings into position to take up the listening, so that the thread of contact is never broken by the turning of the world. The largest of these dishes stretch more than 200 feet across. Great curved bowls of metal aimed with exquisite precision at a target so distant that the slightest error in pointing would lose the signal entirely. Catching Voyager's voice is a little like trying to hear a single whispered word from across an ocean, in the middle of a storm, with every other sound in the world competing for your attention. The engineers must know exactly where to point, exactly what faint rhythm to listen for, and exactly how to pull a coherent message out of a signal so weak it is nearly buried in the natural crackle of the universe itself. That these dishes succeed, day after day, year after year, decade after decade, is one of the unsung marvels of the whole endeavor. Without them, Voyager 1 would already be lost to us, still flying, still measuring, but with no way to share what it learns, a sealed letter with no one left to read it. For now, those great ears on Earth keep listening, straining a little harder each year as the signal continues to fade, determined to catch every last word their distant traveler has to say. You might wonder why it matters at all, this faint stream of data from a place so empty and so far away. The answer is that Voyager 1 is teaching us about a region of space that protects every living thing on Earth, a region we could never study any other way. The galaxy is filled with cosmic rays, particles flung outward at tremendous energies by exploding stars and other violent events scattered across the heavens. These particles are dangerous, capable of damaging living cells and delicate machines alike, and they are constantly washing through the galaxy in all directions. The Sun's great bubble, the heliosphere, acts as a shield against much of this radiation, deflecting and weakening the cosmic rays before they can reach the planets within. Here on Earth, we are protected twice over, once by that great bubble and again by our planet's own magnetic field and atmosphere. But out beyond the bubble, in true interstellar space, the full force of the galaxy's radiation is laid bare. Voyager 1, having crossed the boundary, is now measuring exactly how much stronger that radiation becomes once the Sun's protection falls away. This matters enormously for any future in which humans might one day travel far from home, because it tells us just how hostile the space between the stars truly is, and how much shielding any traveler would need to survive a journey through it. In studying the edge of the Sun's shield, Voyager 1 is, in a quiet way, scouting the path for any who might one day follow, mapping the dangers of a road that humanity has only just begun to imagine traveling. The data, trickling back at a few bits per second, is not abstract or useless. It is a report from the frontier, a warning, and a guide, sent home by the first of our kind ever to stand beyond the Sun's protective walls. There is also a kind of lost art hidden in those old planetary photographs, one worth remembering as we mourn the silent camera. When Voyager 1 sent home its images of Jupiter and Saturn, they did not arrive as finished, polished pictures. They arrived as long streams of numbers, raw data describing the brightness of each tiny point in the image, often gathered through different colored filters at different moments. On the ground, teams of people had to take those streams of numbers and patiently reconstruct them into images, aligning the separate color frames, correcting for the quirks and flaws of the aging Vidicon tubes, and cleaning up the distortions introduced by the long journey home. The cameras even carried a faint grid of tiny reference marks etched onto the face of each tube, a kind of built-in ruler, so that any warping of the image could be measured and corrected by comparing where those marks should be against where they actually appeared. It was painstaking work, part science and part craft, and the glorious images that the world came to know were the product of human hands and human judgment as much as of the spacecraft's electronic eye. In a sense, every famous Voyager photograph was a collaboration, a partnership between a distant machine gathering raw light and a team of people on Earth, coaxing that light back into something the human eye could understand. That collaboration, too, has largely faded into history. The equipment is gone, the procedures retired, the expertise scattered. Even if the camera could somehow be revived and made to gather light again, much of the human craft needed to turn that light into a meaningful picture would have to be rebuilt almost from scratch. The silence of the camera, then, is not only the silence of a frozen lens, but the fading of an entire way of seeing that once brought distant worlds into our living rooms. Spare a thought, too, for the worlds that Voyager 1 never got to see, and for what they reveal about the choice that sent it into the dark. When Voyager 1 was steered close past Titan, it gave up forever any chance of visiting the two outermost giant planets, the great blue-green ice worlds far beyond Saturn. Those distant planets were left instead to Voyager 1's twin, which took a slower, lower path through the solar system and went on to become the only spacecraft in history to fly past both of them. There, years later, the twin spacecraft revealed worlds of astonishing strangeness. A tilted planet rolling on its side as it circles the sun, and a deep blue world wrapped in the fastest winds in the solar system, with a great dark storm churning in its atmosphere. It found a moon circling that outermost world, a frozen world so cold that it erupts not with molten rock, but with plumes of icy material, geysers venting into the near vacuum of space. Voyager 1 saw none of this. By the time its twin reached those distant worlds, Voyager 1 was already far above the plane of the planets, climbing steadily toward the edge of the sun's domain, its planetary work long finished. There is a quiet poignancy in that. The spacecraft that traveled farthest, the one that would go on to cross into interstellar space first and carry our reach deepest into the galaxy, is also the one that saw fewer worlds along the way. It traded the chance to photograph two more planets for the speed and the trajectory that would carry it fastest into the dark. In a way, that trade is the perfect emblem of the whole mission. To reach the farthest frontier, Voyager 1 had to let go of much that lay along the path, choosing the open dark ahead over the familiar worlds behind, a choice that defines it to this day. It is natural to ask whether we could simply send another set of eyes out to where Voyager 1 is now, a fresh spacecraft with a modern camera, to take the photographs that the old machine no longer can. The honest answer reveals just how extraordinary Voyager 1's journey has been. Even with our best rockets and the cleverest use of planetary gravity, it would take a new spacecraft launched today many decades to reach the distance that Voyager 1 has already crossed. The Voyagers benefited from that rare alignment of the outer planets, a lineup that let them gather speed from world after world, and that particular arrangement will not return for well over a century. Scientists and engineers have long dreamed of building a dedicated interstellar probe, a spacecraft designed from the start to fly fast and far, to push deep into the space between the stars and study it directly with modern instruments. Such a mission has been studied and discussed for many years, and it remains a distant goal rather than a firm plan. The kind of endeavor that would take decades to build and decades more to fly. If such a probe were launched in the coming years, it might one day surpass the Voyagers, but not for a very long time. And even then, the very first thing it would do is follow the trail that the Voyagers blazed. For now, and for many years to come, Voyager 1 will remain the farthest reach of human presence, the lonely record holder, the first and still the most distant of our messengers. Whatever we send next, it will be following, in the wake of a spacecraft built with the technology of the 1970s, a machine that flung itself out of the solar system using nothing but careful planning, planetary gravity, and a slowly cooling nuclear heart. That is a humbling thought, and a deeply impressive one. Let us think, finally, about time, because Voyager 1's story is ultimately a story about timescales that dwarf anything in human experience. The spacecraft will fall silent within years, but its journey will continue for an almost unimaginable span afterward. In about 5 billion years, our sun will reach the end of its long life, swelling into a vast red giant, swallowing the inner planets and scorching whatever remains, before finally shedding its outer layers and shrinking into a small, dim, slowly cooling ember. The Earth, as we know it, will not survive that transformation. And yet, through all of it, Voyager 1 will keep drifting through the galaxy, untouched and undisturbed, carrying its golden record with the sound of a child's laughter and the image of a pale blue world that, by then, will no longer exist. Across those same billions of years, our entire galaxy is slowly falling toward its giant neighbor, and in the distant future, the two great pinwheels of stars will begin to merge, reshaping the night sky into something no human eye will ever behold. Even through that grand collision, the stars themselves are so far apart that most will simply sail past one another, and a small object like Voyager 1, lost in the vastness, would likely drift on through it all, unharmed and unaware. The spacecraft may well outlast the recognizable shape of the galaxy itself. It may continue, cold and silent, for hundreds of millions of years, then billions, then far longer still, until the timescales become so vast that words like century and millennium lose all meaning. A simple machine, built in a single human lifetime by a young species on a small blue world, may end up being one of the longest-lasting artifacts that species ever creates, outliving its makers, its planet, and perhaps even its sun, drifting onward as a quiet, enduring testament to the fact that once, on a tiny speck of light, someone looked up and wondered what was out there. When you hold that time scale in your mind, the question of whether to turn on a camera tonight begins to feel very small indeed, and at the same time, strangely precious, a fleeting human impulse set against an almost eternal journey. And perhaps that is the real reason this question stirs something in us at all. We ask what Voyager 1 would see if it looked back, not because we expect a useful answer, but because the act of asking connects us to something far larger than ourselves. We are a species that has always looked outward, that has always wanted to know what lies beyond the next hill, the next horizon, the next dark stretch of ocean or sky. Voyager 1 is that impulse made real. Our curiosity given metal and circuitry and flung as far as we could manage into the night. It carries our questions outward even now, long after the people who first asked them have moved on. And when we imagine it turning to look back at us, we are really imagining ourselves, pausing at the edge of the known, taking one last glance at the warm and familiar place we came from, before continuing into the unknown. That glance, that longing to see home one more time, is one of the most human things there is. The camera may be frozen, the software lost, the power fading, and the distance impossible. But the impulse behind the question, the wish to look back and find that small blue world still shining, will outlast the spacecraft itself, carried forward in every person who ever gazes up at the night sky and feels the pull of what lies beyond. Even now, A few of Voyager 1's instruments continue their quiet work, and it is worth knowing what they still do. The spacecraft can still measure the magnetic field around it, sensing the strength and direction of the faint magnetism that threads through interstellar space. It can still detect charged particles, counting the cosmic rays that stream in from the wider galaxy and watching how their numbers rise and fall. And it can still listen to the plasma waves around it, the subtle ringing and humming of the interstellar gas that has told us so much about the density of the medium through which it travels. These surviving instruments are the spacecraft's remaining senses, the last few ways it still has of feeling the universe around it. One by one, as the power continues to fade, even these will have to be switched off until the day arrives when none remain, and the spacecraft can no longer gather any science at all. The team chooses carefully which to keep alive, weighing the scientific value of each against the precious watts it consumes. It is a slow, deliberate winding down, like dimming the lights in a great house, one room at a time, until at last only a single faint glow remains in a single window, and then that, too, goes dark. There is a strange intimacy in following this process, in knowing that somewhere out in the dark, a small machine is gradually losing its senses, growing quieter and simpler with each passing year, yet continuing faithfully onward all the while. The story of how we knew for certain that Voyager 1 had crossed into interstellar space is itself a small drama worth telling. For some time after the actual crossing, the team was not entirely sure whether it had truly happened. The instrument that would have most directly measured the surrounding plasma had failed long before, leaving the scientists to piece together the answer from other clues. They watched the particles from the sun fall away and the cosmic rays from the galaxy climb, which strongly suggested the boundary had been passed, but they wanted firmer proof. That proof came from an unexpected source. A powerful eruption on the sun sent a wave of energy racing outward across the solar system, and many months later, that wave finally washed over Voyager 1. When it did, it caused the plasma around the spacecraft to vibrate and ring, and Voyager's instrument for detecting plasma waves picked up that ringing. By measuring the precise pitch of the ringing, the scientists could calculate the density of the surrounding gas, and that density turned out to be far higher than anything found inside the sun's bubble. Exactly what would be expected in interstellar space. It was the confirmation they had been waiting for. The spacecraft had indeed crossed the great boundary, and now they could prove it with hard numbers. In a sense, it took a storm on the sun, traveling for the better part of a year, across billions of miles, to ring the bell that finally told us our little explorer had left the sun's realm behind. It was a fitting way to mark such a historic crossing. The sun itself, reaching out one last time to confirm that its most distant child had stepped beyond its protective walls and into the open galaxy. Return, for a moment, to the golden record and to the images encoded within it, because the choices made there reveal something tender about how we wish to present ourselves. The pictures were meant to explain our world to a mind that might share nothing with us, no language, no history, no common frame of reference at all. So they began with the basics, with simple diagrams of mathematics and science, the kind of universal truths that any thinking being anywhere in the universe might recognize. From there, they moved outward to show our solar system, our planet, the chemistry of life, and the structure of the molecules that make us what we are. Then came images of the Earth itself, its oceans and deserts, its mountains and forests, the variety of its landscapes. There were pictures of living things, of plants and animals, of the web of life that fills our world. And there were pictures of people, of human beings, going about the business of living, eating, and working, and learning, building and creating, holding their children, reaching for understanding. The team deliberately chose images that showed humanity at its most hopeful and constructive, leaving out the cruelty and the conflict, choosing instead to present the best of what we are. Some have questioned whether that was honest, whether a true portrait should have included our darker side as well. But the creators made a deliberate choice to send a message of hope rather than a confession, to offer a hand of friendship rather than a warning. They wanted any finder to know not the worst of us, but the best, the part of us that builds and dreams and reaches outward in wonder. That gentle, hopeful self-portrait now rides on the side of Voyager 1, just beside the sleeping camera, drifting outward through a galaxy that may never look upon it. A quiet act of faith in the value of simply trying to reach out at all. And we cannot leave this story without returning, one final time, to the meaning of that pale blue dot, because in the decades since it was taken, that single image has only grown in significance. When people first saw it, many were struck by how small and fragile our world appeared, a tiny point of light adrift in an immense darkness. There was no border visible on that dot, no line dividing one nation from another, no marker of any of the things that so often divide us. There was only the whole of humanity, gathered together on a single speck, sharing one small and precious world. Over the years, that image has become a kind of touchstone, returned to again and again by people trying to express the strange mixture of humility and responsibility that comes from truly grasping our place in the cosmos. It reminds us that everything we fight over, everything we cherish, everything we have ever built or destroyed, exists on that one tiny dot, with no other refuge visible anywhere in the surrounding dark. It reminds us that, as far as we can see, there is nowhere else to go, no other home waiting for us among the stars, at least not any we could reach. And so it carries a quiet plea, woven into its very smallness, to take better care of the only world we have and of one another, since we are, all of us, fellow travelers on the same fragile speck. That plea is, in many ways, the true and lasting gift of Voyager 1's camera. It did not just photograph a planet. It changed, for many people, how they understood their own existence, gently shifting their perspective outward until the petty and the grand alike were seen against the vast and humbling backdrop of space. A camera that took only a handful of truly famous images managed, with one of them, to touch something deep in the human spirit. And that single faint dot of light continues to do its quiet work in the minds of everyone who pauses to consider it. It is worth remembering that the entire journey began with a single, clever realization, made years before the spacecraft was ever built. In the mid-1960s, a young researcher studying the motions of the outer planets noticed that they were drifting into a rare and favorable arrangement. For a brief window in the late 1970s, Jupiter, Saturn, Uranus, and Neptune would all line up along one side of the Sun in such a way that a single spacecraft could visit them in sequence, using the gravity of each to reach the next. This kind of alignment, he realized, comes around only about once every 176 years, a rhythm so slow that the previous opportunity had passed long before anyone had the means to use it, and the next would not arrive until far in the future. It was a fleeting chance, a door that nature opens only rarely and does not hold open for long. That single insight set in motion, the chain of events that would eventually send two spacecraft on the longest voyage in human history. Engineers and scientists worked for years to design machines capable of seizing that opportunity, building them rugged enough to survive the radiation of Jupiter, clever enough to look after themselves across vast distances, and durable enough to keep working far longer than anyone strictly required. They could not have known, in those early years, just how far their creations would eventually travel, or how long they would endure. They were simply trying to catch a rare planetary alignment before it slipped away. And in doing so, almost by accident, they built the first emissaries our species would ever send beyond the edge of the solar system, carrying our questions and our greetings into the dark. The whole improbable adventure traces back to that quiet moment of recognition when one person looked at the slow wheeling of the planets and saw an opening, a chance to reach farther than anyone ever had before. Return, too, to that single day in February of 1990, and to the full scope of what Voyager 1 attempted as it turned for home. It did not take just one photograph that day. It set out to capture a portrait of the entire planetary system at once, sweeping its narrow-angle camera across the sky in a careful sequence designed to catch each planet in turn. In the end, the effort produced a mosaic, a set of frames that together formed the first-ever portrait of our solar system seen from the outside. Looking back across the worlds toward the Sun, not every planet could be included. Mercury was lost in the glare of the Sun, far too close to that blinding point to be safely photographed. Mars showed only a thin sliver of reflected light, too faint to capture clearly. And the small, distant world at the solar system's edge was simply too dim and too far to register at all. But the others were there, strung out along the plane of their orbits, like beads scattered across the dark. Venus and Earth, and Jupiter, Saturn, Uranus, and Neptune, each one no more than a tiny point or a faint smudge of light, each one a world that had loomed enormous to anyone standing upon it, now reduced to near invisibility by the sheer scale of the surrounding space. To assemble it all, the spacecraft had to take dozens of frames, some capturing the planets, others capturing the empty space between them, all stitched together later on Earth into a single sweeping view. It was, in its way, the perfect final act for a camera that had spent its working life showing us how vast and varied the solar system is. For its last performance, it showed us instead how small that entire system becomes when viewed from far enough away. All those mighty worlds gathered into a thin scattering of faint lights, lost against the immensity beyond. One last wonder deserves mention before we close, and it is the simple, stubborn fact of the spacecraft's endurance. Voyager 1 was officially expected to last only a handful of years, long enough to complete its tour of Jupiter and Saturn and little more. Instead, it has now been flying for nearly half a century, far beyond any reasonable expectation, far beyond the working lives of most of the people who built it. Part of the reason lies in the conservative way it was engineered. Wherever they could, the designers built in backups, second copies of critical systems ready to take over if the first should fail, so that a single fault need not end the mission. They chose components that were simple and robust, rather than delicate and cutting edge, favoring reliability over sophistication, knowing the machine would have to survive alone for a very long time with no possibility of repair. They gave it the ability to protect itself, to recognize trouble and retreat to safety without waiting for help that might be a full day away. And they powered it with that slow, steady nuclear heart which asks for nothing, and simply keeps producing electricity year after year as it gradually cools. The result is a machine that has weathered the radiation of Jupiter, the cold of the outer solar system, the crossing into interstellar space, and the failure of system after system, and yet still calls home. It has outlived predictions, outlived expectations, and outlived many of its makers, becoming a quiet symbol of what careful, patient engineering can achieve. There is a lesson in that, one that reaches beyond spacecraft. It is the lesson that things built with care, with humility, and with an eye toward lasting can endure far longer than their creators ever dared to hope, carrying their purpose forward into a future none of them will see. Voyager 1 is the living proof of it, still flying tonight, still faithful, still reaching outward, decades after anyone expected it to fall silent. There is a smaller, quieter struggle that the team has fought over the years, one that rarely makes headlines but speaks volumes about the spacecraft's age. To keep its antenna pointed back toward Earth, Voyager 1 relies on tiny thrusters, small jets that fire brief puffs of gas to nudge the spacecraft and hold it steady. Over decades of faithful service, the thrusters originally used for this task began to wear down, their performance slowly degrading as residue built up inside their narrow plumbing. Faced with this, the engineers made a remarkable decision. They reached back into the spacecraft's design and woke a set of backup thrusters that had not been fired in many decades. Jets that had sat dormant and unused since the days when Voyager was still flying past the planets. Across billions of miles, they sent the commands to fire those long, silent jets. And then they waited the better part of a day to learn whether anything had happened. The old thrusters fired flawlessly, springing back to life as though no time had passed at all, and the spacecraft once again had a fresh way to hold its aim. It was a small miracle of engineering and foresight, the fruit of decisions made decades earlier by people who had thought carefully about how to keep this machine alive far into a future they would never see. In more recent years, the team has faced similar challenges as fuel lines have grown sluggish with age, requiring careful management to keep the precious aiming jets working. Each of these quiet victories buys a little more time, a few more years of contact, a few more reports from the frontier. And each one reminds us that keeping Voyager 1 alive is not a passive thing, but an ongoing act of devotion, a constant, patient effort to nurse an aging traveler through one challenge after another, simply so that its faint voice may continue to reach us a little while longer. There is also something worth understanding about the very shape of the bubble that Voyager 1 has left behind, because it changes how we picture the whole journey. We tend to imagine the heliosphere, the sun's great protective bubble, as a perfect sphere centered neatly on the sun. But it is not a simple ball at all. The entire solar system is moving through the surrounding interstellar gas, drifting through the galaxy at a steady pace. And that motion shapes the bubble, much as the movement of a boat shapes the water around it. On the side facing the direction of travel, the bubble is pushed in, rounded and compressed where it presses against the oncoming interstellar gas. On the opposite side, trailing behind, the bubble may stretch out into a long, drawn-out tail, somewhat like the tail of a comet streaming away from the sun. Voyager 1 left the bubble through the rounded forward region, crossing the boundary on the side that faces into the spacecraft's direction of travel and the solar system's motion through the galaxy. Understanding this shape matters because it tells us that the boundary Voyager crossed is not the same everywhere, that the sun's shield is squeezed and stretched by its passage through the galaxy, thicker in some directions and thinner in others. The measurements from Voyager 1, combined with those from its twin crossing in a different direction, have given scientists their only direct glimpse of what this boundary is truly like, turning a thing once known only through theory and imagination into something we have actually touched and measured. It is one more way in which this lonely spacecraft has transformed a vague picture in our minds into hard, real knowledge, mapping with its own body the very edge of the sun's domain. Pause, too, on what it means that this single machine has woven itself so deeply into the way we think about ourselves. Voyager 1 began as a strictly practical undertaking, a mission to gather scientific data from distant planets, conceived by engineers and approved by committees with budgets and schedules in mind. Yet, over the decades, it has grown into something far larger than its original purpose. It has become a symbol, a touchstone, a shared point of wonder for people who will never understand a single equation about its trajectory. Children who were not yet born when it launched now grow up hearing its story, learning of the little spacecraft that flew past the giant planets and kept going, out past the edge of everything, carrying a golden record and a message of hope into the dark. Its name appears in songs and stories, in films and works of art, invoked again and again as a kind of shorthand for human curiosity and human reach. There is a reason it resonates so widely. Voyager 1 is the part of us that refuses to stay still, the part that always wants to know what lies beyond, given form and flung as far as we could manage. When people learn that it is still out there, still flying, still faintly calling home after nearly 50 years, something in them responds, a recognition of kinship with a small, brave object doing exactly what our species has always longed to do. In that sense, the spacecraft belongs to all of us now, not just to the scientists and engineers who built and tend it, but to everyone who has ever looked up at the stars and felt the same restless wonder that sent it on its way. It carries not only instruments and a record, but a piece of the human spirit itself, the enduring need to reach outward and to know. And so we return, at the very end, to that camera. That small, frozen, silent eye that has not opened since 1990. We have imagined turning it on, and we have followed that simple question honestly all the way to its conclusion. If we could somehow wake it, which we almost certainly cannot, and if we could point it back toward home, which it may no longer even be able to do, it would show us only a sky scattered with distant stars, and it would tell us that our entire world has become one of them, far too small and far too close to the blinding sun to ever pick out. The camera's work is finished, and it was finished well. It gave us Jupiter's centuries-old storms and the impossible volcanoes of Io. It gave us the braided, glittering rings of Saturn and the hidden orange haze of Titan. It gave us the cracked ice of distant moons and the swirling weather of worlds no human had ever truly seen before. And on a single quiet day in February, it gave us the most profound image we have ever made, the sight of our entire world reduced to a pale blue dot, alone in a wandering beam of sunlight, with the vast and patient dark pressing in from every side. There is no real need to turn it on again. It already showed us the one thing we most needed to see. Not the grandeur of the universe out there, but the smallness and the wonder of ourselves in here, on a fragile speck of blue, the only home our species has ever known, drifting through a cosmos far larger and far quieter than we can easily hold in our minds. Voyager 1 is still out there tonight, climbing ever deeper into the dark, carrying its golden message and its sleeping camera, growing more distant with every breath you take. It is the farthest we have ever reached, the longest arm we have ever extended into the night, a small piece of our world traveling where the rest of us cannot yet follow. And though its eye will never open again, the light it once gathered still lingers in our minds, gently reminding us to look after that small blue dot, because as far as we can see in any direction, across all the cold and glittering immensity of space, it remains the only one there is. Thank you for traveling out to the very edge of everything with me tonight. Keep looking up, take good care of one another, and good night.